Today, I'd like to share with you the nozzle dimension control. In systematic failure control, we will start with case studies of actual nozzle-related failure issues, and then discuss the improvement plan for the entire process. First, we need to explain what role the nozzle plays in the placement machine. For example, the nozzle is like our hand. It's the only contact point between the components and the equipment. The strength and stability of the grip directly determine whether components can be smoothly placed on the board. Even minor issues with the nozzle, such as 0.05 mm deformation or 1 mm blockage, can immediately reduce the suction force, causing components to drop. According to industry-wide papers, nozzle issues account for 35% to 45% of all failure problems, making it a critical area that requires close attention. Next, let's discuss the common problems that can occur with nozzles leading to failure issues. I have summarized 7 categories of common problems, which I will explain in detail based on my actual situation in SMT workshops. In simple terms, the nozzle is bent or dented. There are gaps. When it fits the material, if the vacuum is not tight, the absorption will be unstable. It just falls off when you're moving. As for the reason for the deformation, maybe the feeder's locator pin is worn out. Maybe the feed tape is not in the right place, and the nozzle hits the rail when picking up material. It could also be that the nozzle is just soft. The airway was blocked by solid paste, dust, and other debris, causing the air passage in error. As a result, the vacuum state was established slowly, and the high-speed pickup could not keep up. When producing O2 or 1 check capacitors previously known, 7 nozzle frequently reported recognition errors. Upon disassembly, we found the airway filled with yellow-brown dirt. The original 0.8 mm aperture was blocked at only about 0.3 mm, and the airflow speed was less than half of the standard. This was due to the residual solder paste not being cleaned in time, excessive dust in the workshop, and the unreasonable design of the nozzle airway, which allowed impurities to accumulate inside. Another important reason was that the nozzle cleaning frequency could not meet the needs of different environmental conditions. If the nozzle has cracks or gaps, it not only leaks vacuum, but can also scratch the lids of the components. The previous production of 1,206 capacitors had a scrap rate of 8%, and many of the capacitor lids were damaged. Just by looking at the edge of the nozzle, there are fine cracks with a depth of 0.15 to 0.2 mm. And the vacuum leakage rate is more than 30%. This is mainly due to the burrs on the edge of the material strip. When the nozzle picks up the material, it grinds against it. The humidity in the workshop is too high, and the nozzle is corroded. Using large diameter nozzles for small components causes material deviation, while using small diameter nozzles for large components results in insufficient suction. Previously, someone used 1,206 nozzles to pick out 6 or 3 capacitors, resulting in an 8% material rejection rate. The capacitors either couldn't be picked up or were placed 0.2 to 0.5 mm off position during mounting. This was because the program configuration did not follow the nozzle material matching table. Although both types of nozzles were in stockroom management, made it difficult to find the correct nozzle type, leading to deviations from the matching table in processing. After a long time of use, the nozzle becomes rough, and it cannot adhere closely to the material. It will also scratch the material. The yield of packaging QFP for 4 chips is 8%. The pin scratch rate is 5%. Upon opening the nozzle, the inner wall is full of scratches. The surface finish is way beyond the standard, and the suction is unstable, varying from strong to weak. This is because the nozzle was not changed according to its frequency of use. It was still made of ordinary tungsten steel, which is not wear resistant. There have been no daily checks of surface roughness. The nozzle surface was contaminated with oil and grease, creating gaps between the flux and materials. This not only caused vacuum leakage, but also stuck materials. Previously, during O2 or 1 resistor production, the nozzle was not cleaned before continuous operation, resulting in a 6% material loss rate. 30% of components stuck to the nozzle after placement. Inspection revealed 0.05 to 0.03 mm thick residues on the nozzle surface, causing the contact angle between materials and nozzle to exceed standards with significant adhesive force. This was due to failure to clean timely after production, using ordinary cotton cloth for webbing, which left fibers additionally. The excess lubricant leakage from equipment contaminated the nozzle. The gap between the nozzle and suction rod is too large, or there are impurities inside the suction rod. The vacuum leaks from the connection, resulting in insufficient actual suction force of the nozzle. After replacing the overall auto-inductor nozzle previously, the material rejection rate of nozzle 2 was 9%. Upon inspection, it was found that the suction force was inadequate. When disassembling the suction rod, it was full of metal debris. The feed clearance is also beyond the standard. The suction force drops by half from the entrance of the suction rod to the exit of the nozzle because the suction rod was not cleaned before replacing the nozzle, and the suction rod is worn out. The equipment did not detect whether the nozzle was properly installed. Having addressed those issues, you're probably wondering what's the solution. Next, I'll walk you through a comprehensive improvement program. From detection of clean replacement design to training of inventory managers, I will explain everything to you, done by the operator every day before production. Look at the appearance with a 20x magnifying glass to see if there are any problems. Measuring suction with a vacuum gauge. The clearance cannot exceed all 3 mm. Done by the technician every week. Measuring surface roughness with professional instruments. TIPAP tracheal intubation performance assessment. Ensure that the surface roughness is less than or equal to or 5 micrometers. The flatness error is less than or equal to or 1 mm. Done monthly by engineers using the shop floor program and data from the mass system. The nozzle performance and the lifespan are evaluated, with the material rejection rate required to be less than or equal to 0.1% and the remaining lifespan not below 10%. Where conditions permit fully automatic nozzle cleaning machines have been introduced, capable of cleaning 50 nozzles at a time. These machines can automatically accommodate nozzles of various specifications. The cleaning process involves ultrasonic cleaning first, followed by high-pressure spraying, and finally hot air drying. After cleaning, automatic inspection is conducted using industrial cameras for appearance check, vacuum gauges for suction measurement, and airflow meters for air passage testing. Data is directly uploaded to the main system, and only qualified nozzles can be used, while unqualified ones are sorted for further processing. Regarding nozzle replacement and design optimization, different materials require different nozzles, and we can no longer make do with random choices. For small components like O2 or 1 and over O2, we use titanium alloy nozzles with diamond coating, which need replacement every 45 days or after 30,000 users when wear exceeds 0.01 mm. For ordinary components like O6, 03, and 08, 05, we use tungsten steel nozzles with tin coating. Replace every 60 days or after 50,000 users. When wear exceeds 0.02 mm or rejection rate reaches 8%. For large components like QFP and BGA, we use titanium alloy nozzles with elastic silicone contacts. Replace monthly or after 20,000 users. When contact deformation exceeds 0.05 mm or pin squash rate reaches 1%. Design improvements include taper air passages, R-shaping light transitions, and removable filters. The debris is less likely to pile up, and the airflow is smoother. Small component nozzles feature ring-shaped suction grooves, increasing the suction area by 25%. Large component nozzles use 3-point elastic contacts for better sealing. And we have developed a design with universal bodies and detachable tabs. The number of nozzle types has been reduced from 15 to 5, cutting inventory costs by 60%. Nozzle searching has become much more convenient. Along with improved inventory and traceability management, we engrave QR codes on each nozzle containing information such as model, equipment number, and procurement batch. From storage to maintenance, the entire process is traceable. We no longer need to worry about lost or mixed nozzles. Smart shelves with weight sensors and infrared sensors are used for inventory management, automatically warning of low stock. Monthly inventory checks can be done by scanning cards, with discrepancies controlled within 5%. Personnel training is also crucial, with different training contents for operators, technicians, and engineers. Operators need to learn how to inspect nozzles and operate cleaning machines. Technicians need to know how to repair nozzles and adjust parameters. Engineers need to analyze data and optimize solutions. You might be wondering how effective these measures will be once they're implemented. Let me share some improved data with you. The average reject rate for the nozzle is between 0.08 and 0.1%. The rate has fallen to between 0.05% and 0.08% after the reform, a drop of 50%. The nozzle lifespan has doubled from 1 to 2 months to 2 to 4 months. The automated cleaning pass rate can reach 99% to 99.5%. While the nozzle loss rate has decreased from 0.5% to 1.0% to 0.05% to 0.1%. Labor costs for nozzle management have also been reduced by 80%. The labor cost of managing the suction cups also dropped by 80%. It used to take 5 people to change them every week. So now 1 person can do it. Of course, improvement is not a one-time solution. We conduct technical analysis monthly, review data, and address high-frequency issues. Quarterly, we benchmark against large enterprises like Huawei and Foxconn, learning from their advanced technologies and introducing AI models to predict nozzle wear time, aiming for a 95% prediction accuracy rate. Our goal is to achieve 0 defects and 0 material rejection for SMT nozzles, make production smoother and reduce production costs. And that way, you're also working a lot less. I hope you can apply what we have discussed today to your actual work and solve the problems of nozzle and waste material throwing in the workshop completely. All of the above is my personal opinion. If you found my content helpful, please subscribe my channel and follow. Thank you for watching and see you next time. Bye.